Okay, we're now going to look at the more complicated case of reflection and transmission for plane waves that arrive on the surface at an oblique angle. So how are we going to do this? Well, again, we're just going to solve Maxwell's equations expressed in the form of the boundary conditions between the two interfaces. So once again, we put an interface on the plane z is equal to 0, and we write our incident, reflected, and transmitted waves as monochromatic plane waves. We consider a single frequency. So what have we got? It's a slight generalization from what we had before. So for the incident wave, if we look at the electric field, first of all, we put it as a function of the full 3-vector positional variable r. Now, there's a vector here that represents the electric field vector. We haven't decided yet in which direction the wave is polarized, so this is still a vector. Now, in the plane wave expression, there's now a k incident, which is a vector dotted into r with omega t. We've seen for plane waves that the magnetic field is just given by 1 over the velocity of propagation direction crossed into electrical field. So the magnetic field is perpendicular to the electric field, and both are transverse to the propagation direction. Okay? The reflected wave has a very similar expression to the incident wave. The only replacement that we've made is that we've got now a reflected wave vector here that we'll have to characterize a bit more. For the transmitted wave, exactly the same thing, except that now we have propagation in medium 2, which means that the velocity that appears in the expression for the amplitude of the magnetic field contains velocity in second medium. Okay, so we're just going to use this ansatz again, this kind of trial form for the electromagnetic fields in our setup. Okay, so once again, I've kind of written a few equations for you to accelerate the argument. Let's look first of all at the wave vectors. Let's look at the amplitude of the wave vectors because that's the simplest. And we know that for monochromatic waves, we have this relationship between the frequency, the propagation velocity, and the propagation wave vector. In our case, this has to hold for all the incident, reflected, transmitted waves. So we have that V1 times the incident wave vector amplitude. So here I'm using the notation where just the norm of the incident, reflected, transmitted wave vector is just written by this simple letter. So the norm of the incident wave vector times V1 is equal to the same thing for the reflected, but now for the transmitted there's a V2. So the norm of the incident reflected wave vectors is the same, and the one of the transmitted one is modulated by the ratio of the indices of refraction between the two media. Okay, so that's the first thing that gives us the length of the vectors. Now, we are trying to solve our boundary conditions, and our boundary conditions, I remind you, we had written them down a little while back. Our boundary conditions are just the same. We still have precisely these 4 equations coming from integration of Maxwell equations on Gaussian pillboxes or Amperian loops around the interface between the two media. So we still have this. But of course, when we put our expressions that depend on all coordinates of space and time into this, these are all instantaneous equations, the same point in time. If we imagine looking, for example, at this equation here for general x and y dependence, in this case z is equal to 0, but if I have completely arbitrary x and y dependence here, then the x and y dependence has to factorize in these two terms. It has to be the same. And in our case, once again, on one side of the boundary, on the side 1, this is composed of the electrical field amplitude of the incident and reflected waves. And in the two side, it's just the transmitted waves. But if I look at the spatial dependencies that I've defined for these things here, the x and y dependencies have to be the same. So since these boundary conditions must hold for any x and y, I must equate the x and y components of the incident, reflected, and transmitted wave vectors. And that has a very, very strong consequence because it means that indeed these incident, reflected, and transmitted wave vectors they are on the same three-dimensional plane, this two-dimensional slice of three-dimensional space, which we call the plane of incidence. Okay, so when we draw the situation like this, this is now our surface. The transmitted wave is here, the incident wave is here, but now these three rays are in the same plane. And we can, if you want, choose our coordinate axes to simplify our lives a little bit, but we'll do that in a second. So that's the situation that we have. We have the incident wave coming at a certain angle, theta I, with respect to the normal. The reflected wave comes out. The transmitted wave goes into medium 2 like this. Okay, so this is where we start from. Okay. Let's get going on this, because we already have the conditions that we need. Okay. Let's see. So we have this rule here, and if we look at the consequences of this rule, what we get, so essentially this one here, specialized to these notations here, what it tells us is that if I take so once again the components that we have here have to be equal. Yeah, so all these conditions here, what does it tell us? It tells us that if I like project the wave vectors here with these angles, they have to be equal. So what does that tell us? It tells us that the incident wave vector times the sine of the incident angle, that has to be equal to kr sine theta r, and this has to be equal to the k transmitted times sine theta t. So what can we get from that? Well, first of all, because ki is equal to kr, then theta I has to be equal to theta r. So that's the first thing. Theta incident has to be the same as the reflected, or reflected has to be the same as incident. Okay, and this is simply the law of reflection. Okay, and the second thing that we know, substituting this one here in here, is that if I do n1 times the sine of the incident wave, this has to be equal to n2 times the sine of the transmitted wave angle. Okay, and this is the law of refraction, which you might also know as Snell's law. Okay, but it's kind of nice because we have derived those laws now from Maxwell's equations. Okay, but let's go a little bit further so we get all the details sorted out correctly. Okay, so what we've done here is really take care of the xy dependence of everything. So now all these things are sorted. Okay, and now what we want to do is really specify all the components of our vectors. Okay, so maybe I'll do it cleanly from this. You see, so from the boundary conditions, we can write the following set of equations. So we have that epsilon 1 with the amplitude of the electrical field on the one side, so this is E0I plus E0R, and now I remind you these are vectors, okay? And now the Z component of this, because we're doing the first boundary condition, which is about the perpendicular component of the electrical field, this has to be epsilon 2 with the vector E0T, again the Z component of it. So that's one of them. The second equation just tells us that the magnetic fields are continuous, at least the perpendicular, so B0R, again Z component. This is equal to the transmitted magnetic field Z component, so that's the second boundary equation. The third one tells us that E incident plus reflected for any x or y component has to be transmitted, any xy. And finally, the last one, 1 over mu1 b incident plus b reflected, any xy component has to be 1 over mu2, the transmitted magnetic field vector, any xy component. Okay, so you see now we come to the delicate situation of finding different dependencies depending on the orientation of the electrical field of our wave. So depending on how the electrical field is oriented as compared to the plane of incidence, we can get different results. What we're going to do here is treat the simplest case of polarization, that is orientation of the electrical field. So polarization in the plane of incidence. Okay, so the electrical field of my incoming wave will be taken to be inside the plane of incidence. Okay, if you do that one, and you do the if you want conjugate one of being perpendicular to the plane of incidence, then by linearity you have a general solution. But we'll just do the simplest case first. Okay, so in that case, if I look at the first equation here, then I can rewrite it in the following way. So this first equation here then tells me that epsilon 1, with now I will just do minus, so I do the projection onto the z-axis, E0i, so this is now a scalar, right? I'm projecting the coefficient along the z-axis, which is the sign. Minus sign is because of the choice that I have of putting the electrical field this way. Okay. Plus then E0r sine theta r. I'm not substituting yet theta I is theta r. I'm just writing the boundary condition as is. This is minus epsilon 2. E0 transmitted, again with the sine of theta t. Okay, so if I just look at the second equation, that's a trivial, I mean, it's 0 anyway. So there's nothing there because I know that the B field is perpendicular to the plane of incidence. Okay. The third equation, this one here, it tells me something different. It tells me that E incident with now the cosine of theta I plus the reflected bit, which is again the cosine of theta r, is equal to just the transmitted with cos of theta transmitted. Okay? And the fourth equation, this one here, again, this gives me the non-trivial condition that 1 over mu1 times v1, because you remember the magnetic field amplitude is 1 over v, the electrical field amplitude, and now I've got E OI minus E reflected. This is equal to 1 over mu2 v2 with the transmitted electrical field. So E over v, once again, is the magnetic field amplitude. So that's just this one here. Okay, so now we know the laws of reflection and refraction. So theta r is equal to theta I. Sine theta t is just n1 over n2 sine theta I. So we can just substitute that into our equation. So let's see what we get. Okay. Now, if you look at the at this equation here, it becomes the same as this one here when you substitute the law of refraction into this one. And what does that tell you? It just tells you that E incident minus E reflected is equal to, again, just recognizing our factor beta. You just put the mu1 v1 here, and that becomes the beta. So this is just beta, the transmitted amplitude, like this. Okay? So that's equations 1 and 4, which are just the same equation in the end. Now, this third equation tells us a different thing. It tells us that E incident plus E reflected is equal to some ratio of cosines, right? So this cos theta t divided by cos theta I times the transmitted amplitude. Now this ratio here is kind of a handy ratio. We will call it alpha. Okay. So if we just solve this, once again, for writing the reflection and transmission amplitudes in terms of the incident ones, what we get are the following two equations. The reflected amplitude is just alpha minus beta over alpha plus beta times the incident one. And we get that the transmitted one is equal to 2 over alpha plus beta with the incident one, like this. Okay, and these are known as the Fresnel equations. And here they're specialized again for the polarization in the plane of incidence. Okay? So these are extremely important. They're a generalization of what we already had for normal incidence, because you see, if I arrive normal, then my incident angle is just 0, and this ratio is equal to 1. So I fall back to 1 minus beta over 1 plus beta, which is exactly what we had before, 1 plus beta here. Okay? So this is just like a generalization of what we had done for the normal incidence calculation. Now, the little ratio alpha, we can rewrite it in a slightly different way. So let's look at this ratio alpha. Well, we can write it this way because it's cosine. I can just use this identity here, 1 minus sine squared theta t. Okay, and then a nice little square root here, and this whole thing divided by the cosine of the incidence angle. Okay, and I can use the law of refraction here to express alpha exclusively in terms of the angle of incidence. Okay, so just substituting the law of refraction for the sine squared here, I just get that this is 1 minus the ratio n1 over n2 squared with the sine squared of the incidence angle, and all that inside a square root, and all that, of course, once again divided by cos of theta I. Okay, so this is nice because I only need the incidence angle to determine exactly everything in the reflected transmitted amplitudes and therefore intensities. Okay, so once again, for theta I is equal to 0, this just goes back to what we had before. If I were to take the incidence angle to be like pi over 2, so I'm really just having a wave that comes grazing my surface like this at a very, very, very shallow angle as compared to the surface here, then what happens? Well, this this alpha, it goes to infinity, right? Because my cosine is going to go to 0 plus. And this thing here is strictly positive. Here, if the ratio of these two things is different than 1, I maintain a finite number here, so alpha goes to infinity. But if alpha goes to infinity, then the reflected amplitude is essentially the incoming amplitude, whereas the transmitted one goes to 0. Okay? So what I get here is I get a total reflection. So that's one thing. Grazing incidence gives you total reflection. Alternately, there's also another really cool angle. So alternately, if I look at my reflected wave here and I arrange things so that alpha is equal to this beta, so beta being a property of the two media, but alpha being a property also of the incoming angle, I can adjust it. If I were to choose an angle such that alpha is equal to beta, there would be no reflected wave. And everything would be transmitted. Okay? So this angle is known as Brewster's angle. So Brewster's angle, you can just write it. So theta Brewster is just the arc sine of, putting the condition alpha is equal to beta, so the arc sine of 1 minus beta squared divided by n1 over n2 squared minus beta squared, and all of that in a square root. Okay, here I'm literally putting alpha is equal to beta, using alpha is here, and just taking the identities that I have. Okay, so that's a really cool angle at which there is pure transmission, no reflection whatsoever. Okay, just some final notes. The power per unit area so hitting your surface, striking the surface. So what is it? It's really just the pointing vector dotted into the normal unit vector for your surface. So you just get that the incident intensity is epsilon 1 v1 over 2 E0I squared with the cosine of theta I, and then similar equations for the reflected and transmitted. So R, it's still epsilon 1 v1 over 2, but now just the reflected intensity amplitude squared cos theta R, which is theta I, and the transmitted one apologies, epsilon 2 v2 E0 transmitted squared with the cos theta t, which is again a function of the incident one. So the for the coefficients of reflection and transmission, what we have is once again R is just the reflected versus incident intensities, and then it's just simplifying to this ratio, so this becomes alpha minus beta, over alpha plus beta all squared. And the transmission coefficient, once again, the intensity in the transmitted wave versus the intensity in the incoming wave. So that's just, again, the ratio of this versus this, epsilon 1 v1 with epsilon 2 v2. So when you actually put it together, rewrite it in terms of alpha beta, you just get something quite similar to what we had before. You get this here. So once again, r plus t, again, equal to 1 as expected. Okay, now there would remain to treat the case of polarization perpendicular to the plane of incidence, but I will actually leave that one to you as an exercise.